Okay, lecture 5. Now let's look at this. I'm going to take a tangent for a second. Talk about final value theorem. So let's, if we were given this, remember, and we were asked, okay, what's the final value? Can we apply the final value theorem is one question. And what does this circuit settle out to when t equals infinity? So if you remember the final value theorem, first thing you got to ask is, so for the final value theorem, does the roots or the poles, which are the roots of the bottom, of s times s of s all lie in the open left half plane. So s times x sub s would be s times 5s plus 3 over s plus 1, s plus 2, s plus 3. And here the poles are at s equals minus 1, minus 2, minus 3. So all the poles lie in the open left half plane. There's none on the j omega axis, and there's none that are to the right of the j omega axis. So if you remember, the final value theorem said, okay, well, I want to find out what x of t equals when t equals infinity, and that is the limit of s times x of s as x approaches 0. Let's see if we can see what that would be. So I've got 0 times 5, 0 plus 3 over 1, 2, 3. Because of that 0, the answer is 0, right? We'll go up here and look at this. What happens? We'll go up here and look at this. What happens when, does that make sense? What happens when t grows larger and larger and larger? Well, e to the minus t, is going to look, it's going to trail off. E to the minus 10 is a very small number. E to the minus 100, e to the minus 1,000. That's going to approach 0. Similarly, this is going to approach 0, and that's going to approach 0. So yeah, the final value theorem, if all you were asked is what is the value of x of t as t approaches infinity, you could have done it two ways. You could have either done partial fraction expansion like we did, got the inverse Laplace transform like we did, and let t rise, and you can see that all the terms go to 0. Or you can, if you're given this in the frequency domain, you can look at the poles, see if all the poles are in the open left half plane, and solve for the limit as s equals 0. So in this case, much easier to use the final value theorem. And you can see it kind of makes, when the poles are in the left half plane, so like in this case where we have a pole that's here at minus 1, the fact that this pole was at minus 1 made this be minus 1. The fact that this pole was at minus 2 made this piece be minus 2. And this pole was at minus 3 made this part be minus 3. And those pieces are the ones that made this approach 0. If this pole was in the right half plane, if this was s minus 1, or this was s minus 2, s minus 3, if any of these poles were in the right half plane, the sign of this or this would have changed. And therefore, this would have been e to the t, which would have grown without bound. And so you don't know what the limit is, because it doesn't approach a single steady state number. So that is why the poles must be in the open left half plane. And kind of like what I commented in class today, if it turns out that you have poles that are on the j omega axis, then you will end up with the inverse Laplace transform will turn out to be a sinusoid, and it won't approach a single number. All right, so that's applying the final value theorem to the piece we just looked at.